And before we get started, I have a few announcements. So next Wednesday, we'll be having a work in progress talk, Francis Harper, at the same time, 12 noon in 133F Erickson. And the next external seminar talk will be Lima Berland, again noon on the 5th of November in here. If you'd like to,
seats in the front if people are coming in.
If you would like to sign up to talk to her, please contact Christina Schwartz. Now to the main event. It's my distinct pleasure and honor to introduce Helen Quinn, who I actually probably needs no introduction to most people in the room. Helen has had a long and illustrious career in high energy physics. She has been awarded many prizes. She's a member of the National Academy of Sciences. She holds both the Dirac Medal and the Klein Medal. And but that's not why she's here. She's here because after she conquered high energy physics, she decided she would actually take on a more difficult task, which is to transform education. And so Helen has been instrumental in many initiatives. She has been the chair of the Board on Science Education of the National Research Council. And she was also the chair of the committee that developed the framework for science education that was published in 2012 and from which the NGSS were based on. And without further ado then, I'd like to introduce Helen and have her talk to us about cross-cutting concepts.
So there's an assumption in the title, which is that all of you know what a cross-cutting concept is. Right, so let's start with that. I'm talking about the cross-cutting concepts as they're defined and represented in the framework for K-12 science education, which, by the way, I think applies to a lot more than K-12. So the idea is there that science has three dimensions. The dimension of core ideas in the disciplines, which everybody calls content, although I think it's all content. The dimension of science practices, what you do when you're doing scientific inquiry, and what students need to do as they learn science for two reasons: to understand what science is, and to actually go through the process of conceptual change that allows them to really incorporate the science thinking into their thinking and problem solving in new contexts. So, and the third dimension is the thing we call the cross-cutting concepts. So I'm going to talk today about why they're there and what I think they're for and how they can be used. Please come up to the front. There's a couple of chairs at the front here. And it will be more of a discussion than my telling you all the answers, because I don't know all the answers. However, I do know that even if you go back, I like to go back to the 19th century when high school science was defined as physics, chemistry, and biology. And if you think about it, in the 19th century, those were completely separate subjects. They had nothing to do with one another, essentially. Maybe thermodynamics began to connect them at that point, but they really were separate views of the world and separate things. Why were they all called science? What was common to them that made them all science, right? And that is science practices and this set of cross-cutting concepts, which I think of as thinking tools. Things you need to think about to address new problems. And so thinking of these as conceptual tools when meeting an unfamiliar problem, and conceptual tools which are common across all of science, although exactly the way they'll play out is different in different areas of science. Each of them has uses across all areas of science. And that is why we call them cross-cutting. That means that for students, there's again, it's like the practices, there's two reasons why they need to be there. One is because they're useful thinking tools and they need to learn those tools. And the other is because part of understanding what is science is understanding what is it that's common across disciplines, and how do I connect ideas I'm learning over here to ideas I'm learning over here in two separate science classes. And these cross-cutting concepts are part of what make those connections possible. So that's the way I view it. And what I'm going to do, if you're faced with a problem, what's the first thing you need to do? You need to ask some questions to figure out what's going on and what it is you're trying to solve. And so what I'm going to do is turn the cross-cutting concepts into a set of questions. Questions which can be used in pretty much any context to follow up and take these ideas and apply them in the context of whatever science problem you're facing. And I'm going to present the first one and tell you my version, and then we're going to work together on the later ones. Okay, so the first on the list, I'm figuring out how to advance this computer, is patterns. So the idea is that it's useful to notice patterns because figuring out why those patterns appear begins to give you good questions to ask and good ideas about whatever it is you're studying. So the two general patterns questions I put here: what do I notice after careful observation? Do any features or patterns emerge that are interesting enough to need further study? And what particular patterns, what repeated patterns in time, patterns in space, shape features, what do I notice that repeats and therefore needs explanation? Right, so those are the general patterns questions. And now you say, but where do they fit? So I decided I'd think about, well, how do we use these ideas about patterns as we engage in the science practices? So that's another list that I expect you all know. And most of you probably do by now. So I'm going to go through a set of secondary questions about patterns that link one by one to the practices. So I can ask, for example, what questions do I have about these patterns? And that will generate interesting questions about what I'm studying here. Or what features of these patterns can I explain with my model for the system that I'm studying? And if I can't, how do I need to modify my model so that it does reproduce the patterns? Right? So the patterns tell me they need to be explained. If my model doesn't explain them, maybe that's an inadequacy in the model and I need to go revise and refine the model. We can ask, what do I need to investigate further? How do I clarify my thinking about these patterns by really defining an investigation I need to do? And then, how can I organize and display my data so that these patterns are represented in my data display?
Would you like to use a remote?
It'll make it easier, you won't trip.
As long as
Just
he's worried about
plug in
my...
the USB.
Okay.
All right.
I mean,
Put it in the computer
just
and
stick in the
do this,
USB.
and then I'll go backwards instead of forwards, but that's all right.
Yeah, you won't trip over the cord.
So, you see, practice by practice, there's a question about patterns that amplifies how I take the idea of patterns and play it out in this practice. Right? Can I find a mathematical description of the pattern or a computational way to implement representing the patterns? That's mathematics and computational thinking, right? Can I explain the causes of these patterns? How do my explanations of the patterns work? Right? And how do the patterns help me explain other aspects of the system that I'm talking about? Or if I'm doing engineering design, what patterns would I like my design to produce? So again, just taking the theme of patterns, the cross-cutting idea of patterns, and going practice by practice, you can see in each case you find a way of bringing the concept of patterns are interesting, a step further to say, all right, but I need to investigate further, or I need to explain more, or I need to design something. And in each case, having concepts around patterns in mind can inform the process of that next step. Can I use these patterns as evidence to support my claims about the system in question? Or what information can I obtain that will help me better interpret these patterns? How can I communicate my observation of these patterns to other people? So you see, I've gone with patterns through every single practice, and in each case, it gives me a question which helps me implement the practice when I'm looking at a problem that I haven't really seen before, and I need some ways to dig in. And if patterns are the thing that comes up for me when I'm looking at this problem, then this is the way to take the idea of patterns and take it into the practices and use it further. So, in my mind, questioning tools are really what I'm developing here. And tools for students to use an idea over and over again in different contexts, which is what they need to do to make it an idea that they actually own and can use on their own in some new context. And that's what I think the cross-cutting concepts are. They're tools for making connections and tools for thinking about problems. And I know, there's 7 cross-cutting concepts and 8 practices. It's a huge table of how they multiply up. So not every cross-cutting concept really connects well with every practice. Some are more linked to one specific practice. But for this one, it actually translates across all of the practices. Whether the others do or do not, that's something I leave for you to think about. But in this case, I think it's worth doing this the first time to see this is one of the ways to use these to bring them into the practices. Okay. I think when you look at them overall, you notice that, so this is the rest of the cross-cutting concepts, there's more direct linkages, right? So each of these cross-cutting concepts links to a particular practice more strongly than it links to the other practices. You could argue about, is stability and change about developing models or about developing explanations? I would say it's about developing explanations, because in order to start thinking about stability and change, you have to already have your model. You have to be thinking about a system, and you have to ask, under what conditions is this system stable? So in each case, this is my strongest linkage. You may see other ones as well, but I think each of these are important. So you notice that developing models appears multiple times. And developing explanations, which I consider as the next step after developing models in a sense. I don't see how you can develop explanations without first having developed the model. So, because your explanations are relying on a model, whether it's implicit or explicit, and better make it explicit. So this is my argument that there are, in fact, for each of these linkages to the practices. Now, why do we need a practice of developing models and a cross-cutting concept of systems and system models? Wasn't it good enough just to have the practice? I think not, because in order to engage well in the practice, you have to have some concepts. You have to have the concept of a system, and you have to have the questioning tools about systems, which we'll come to in a moment, that you need to ask as you start trying to develop a model of a system. You can't just sort of blankly look at a system and a model appears. You have to have a process for defining your system and developing the model. And so sometimes the process is just implicit. We learn it by practice, and we do it again and again, and eventually we know how to do it. But sometimes it's really useful to have some tools that help us do it, and some concepts about what it is we're trying to achieve. And so the need for both a practice and a concept. It's also true with the engineering, right? We have engineering practices and we have a core concept on engineering design. Again, it's because you need to know something and have some ideas about what you're trying to do in order to do effectively. Okay, so this one's blank. I want you to talk to the person next to you and think about some questions about cause and effect that you might ask when given a system to understand. Just 2 minutes of talking. I'm going to be quiet. So I want to see people talking.
That's something, the fact that this is cross-cutting will allow you to develop greater skills.
Okay, I'm gonna stop the conversation.
Conditions
Anybody want to throw out a question or two
equally important.
that we came up with? Somebody have a question? All that talking and you didn't come up with, yeah, okay.
We had, how does your model explain cause and effect relationship?
Okay. Yes.
Well, one nice thing that cross-cutting themes and concepts can do is allow you to link two different contexts and see variability. So one question is how is cause and effect and an explanation related to it different perhaps in a physical system versus something a computer could lead you to, which would be a case in maybe a biological.
So how does it differ? How does cause and effect look different in physics and in chemistry and in biology?
Different and same. Subtlety
Right.
of use.
So I would say I'm looking for something simpler. When the student is first meeting cause and effect in one context, how do you get them thinking about cause and effect? Once they're thinking about cause and effect, then seeing that cause and effect is what you're thinking about in chemistry and cause and effect is what you're thinking about in biology, but it looks very different, is a sort of a second step. And I think that's one of it. When we say cross-cutting concepts, yes, they connect, and yes, they are common across the discipline. But I think in teaching them, that's probably not where I'd start. I'd start with, how does this idea play out in this context? And then seeing that the same idea plays out in many different contexts is the connect. Then you start talking about connections. So, but that's an interesting question, right? How does cause and effect look different when I'm thinking physics and when I'm thinking biology? Or is it not different?
Exactly.
Okay, anybody else have something they wanted to throw out as a cause and effect question? Yes.
which is the cause and which is the effect? I mean, sometimes in biology, we can't always tell.
Untangle. So when we're talking about cause and effect, we sort of are thinking as if there's a time sequence. That's the physicist's view of the world, right? So this happened first and that happened later. Did this cause that? But yeah, sometimes when you're looking at something and you don't have that time sequence information, figuring out relationships like cause and effect are not so obvious. So let's go to what questions I had put there. Really the first one is, why did that happen? Right? That's the cause and effect question. Is there some reason, is there some mechanism by which I can explain why I'm seeing what I'm seeing? And so thinking about what kinds of relationships might be cause and effect relationships. Thinking about what do I need to explain about those relationships. I think actually we titled this one wrong. We should have called it Mechanisms of Cause and Effect, but mechanism sounds too physical because it's not about that things have causes and causes have effects. It's about trying to figure out what is the relationship between A and B that could possibly mean that A causes B. It's part of untangling the difference between causation and correlation, right? Or in engineering, you want to have an outcome. You want a particular cause effect. So how can I design my system to cause that effect? Is an engineering question.
So Helen, I want to take in your third question. And to me, that's more related to modeling. So when I'm trying to help people understand what a model is, I would ask, to what extent does my model provide a causal account or a mechanism to explain some phenomenon?
Yeah, so you're doing,
Right.
you're using modeling to bring out the cross-cutting concept of cause and effect.
That's right.
And I'm talking about it the other way around, saying I can use the idea of cause and effect to test my model. Right, so both ways work. Both ways work. But it's a connection, certainly, that when you're trying to model a system, the model should have explanatory power for something. And one of the somethings is the causes of effects that occur in, or the causes of phenomena that occur in that system. And so, indeed, modeling is one of the tools for getting to understanding of what caused, when you look at a phenomenon, you say, how did that happen? Why did that happen? Now you need your model to begin to understand how and why that happened. So yeah, they're very intimately linked. So cause and effect is about modeling and explanations.
Right, so I agree with this, but the reason I actually also wanted to point out is in your previous slide under cause and effect, you didn't have modeling. And that kind of surprised me. You had explanation. Now,
Right.
Talk. Otherwise, maybe you didn't have it there because otherwise it'd be modeled.
Well, I would put models everywhere. Yeah, I mean, to me, modeling is so fundamental. If you talk about systems and system models, you need those to develop explanations. You need those to, and explanations of cause and effect need models. I completely agree. And yeah, we could put them all under modeling to start with, because they all play a role in modeling, but, okay. Let's go on. This one's harder. This one, first of all, it's not one idea, it's three ideas, which are sort of interrelated, but not exactly. Why is it there? Partly because this is a place where students struggle, right? And quantity to me in science means something you measure, right? Which means it comes with some units, right? It is a quantity for which there's a scale and you can measure. And one of the things that students struggle a lot with is understanding the role and meaning of those units and how they interconnect. So, and I talked with the graduate students this morning, I bring up the idea, we wonder why students can't take their math and use it in science. And we tell them, density is just a ratio. But it's a ratio of mass over volume, which are two completely incommensurate things. Whereas all they know in math is a ratio of number over number, which can be represented by fractions of a pi. Right? So the translation from math to science needs understandings related to quantity, to scale, on what scale do I need to measure things, and how does the system scale when I change the scale. To proportion, like ratios of mass over volume, or proportions, which are a fundamental idea in beginning chemistry or stoichiometry, right? I mean, chemistry was discovered by understanding proportional relationships, and we need to help students understand it. So those are the places where it plays out, how you get students asking questions related to this. So once again, I'll give you a couple of minutes to think about it and talk for yourselves, and then I'll put up the ones I came up with. If this gets boring and repetitive, we can stop doing it, but try again for a few.
What do you do? Last time, so why don't you start
Here's my version, and then I'm going to ask for some of yours. I'm doing it the other way around this time. So I said, what aspects of this system do we need to measure or quantify in order to describe it more precisely? That's a question you can ask in any area of science. It doesn't mean that what you measure connects the different disciplines of science. But the fact is, this is a question which is important no matter whether you're looking at an ecosystem or an organism or a machine, right? These things are questions you have to ask. On what scale, with what units, and to what precision do I need to measure it? So this is really, maybe we should have called the cross-cutting idea measurement. But the idea of scale is more than the idea of measurement, right? The idea that when we're describing the human body, we can describe it on the scale of lungs and circulatory system and digestive system or whatever, or we can describe it on the scales of cells, or we can describe it on the scale of biological macromolecules. And at each of those scales, there are questions we can answer and things we can understand. And in fact, one of the things you want to develop is the ability to think back and forth across scales and to connect what's going on at the smaller scale to the larger scale to the larger scale. So having scale concepts in mind so that students understand that an atom is much smaller than a cell, right? And that a cell is much smaller than a heart, right? Having some sense of scale is really important to understanding what you're talking about here. Yes?
Right, and this seems, as you go from measurement to the other issues related to scale, you introduce the question of what are the dimensions of difficulty in learning this, and sometimes the measurement issues are straightforward, but the conceptualization issues are difficult. For example,
Absolutely.
evolutionary time, which is very hard.
Very long times are very, very hard to conceive.
But not hard to measure.
And not actually hard to talk about
Yeah.
once you know them, but conceptually. they're just-
Exactly.
The whole problem with evolution is how long it took to happen.
Exactly.
Right, and understanding things like that requires you to have a sense of scale.
A sense of
Right.
scale.
To be able to recognize that 5.6 billion years is
Exactly.
different from 500,000 years.
Yeah. So you would think of
Okay.
visualizations here as a way to help that. How does that fit into this scheme? What you would do to make
Well-
scale more easy to understand?
You see, my idea with every one of these cross-cutting concepts is that if we introduce it early enough and introduce it very, very simply and then build on that and build it up, by the time we get to the students in college here, they will have this tool to be able to use. And that will help them understand the science you're trying to teach them at the college level. But if you're starting at the college level and they don't have it, then it's a lot of work to develop it, right? And so this is the reason all of these things are made explicit as things that need to be thought about as you're teaching even very young children, right? Trying to develop where is it that kids learn to use mathematics and science? And how do you introduce ideas of scale to them? And once, you know, the Scientific American Powers of 10 movie? I had a friend whose child, I think, was really a slightly autistic child. And that movie, at 5 years old, was the one thing that fascinated him in the world. So these ideas of... It's fascinating, it is fascinating, right? The idea that all these, every time I mean, once you can understand that 10 is much bigger than 1, right? And that if you have 1 and this is 1 and this is 10, right? You could go 10, 10, 10. It's an unbelievable opening up of views of the world and things you can think about. And then you can go from the universe to the tiniest thing we know. But there's many, many, many powers of 10 between those things, and conceptually, it's very hard to visualize.
That gets at the distinction I was trying to get at before. You have a language like measure it more precisely, but then before you also talked about a sense of scale, and the powers of 10 gets a bit more at the sense of scale.
And
than
that's
at the
important
measure.
too, right?
Yeah.
So I think you have to go back and forth, and that's why I say this is not just one thing. Scale is one thing, and proportion and quantity is really another thing. And we put them together because they're all about quantity in some sense, but conceptually scale, I'm thinking about scaling and how things change as you go by factors of 10, what you can see or not see at a different scale. That's very different from actually measuring. Although actually, to talk about it, you have to be able in some sense to measure on all those scales.
Right.
It's very interesting to ask, you know, how do we know how far away a star is? Right? We talk about the expanding universe, and we say the stars are getting further apart. How do we measure that? And then for engineering, of course, the idea of a scale drawing and a scale model is a different use of the word scale in a sense, although it's closely related. And in engineering, these are very important concepts. An engineering model, by the way, is different from a science model. Right? Engineers may use science models, but when you talk about an engineering model, you mean something used to test a design. All right, systems and system models. Joe agrees with me that modeling is important, and of course you've got to model something, so you have to define what system you're looking at. How do you go about doing that? What questions would help students, given a phenomenon, figure out what system it is they're going to be looking at? Want to talk? Or you want to just go on? Talk. You learn more when you think, you know.
Same thing we did before, except now with systems and system. We didn't know exactly what we were before, so that doesn't necessarily help us.
What is the model?
One basic question is, when you talk about systems and say levels analysis, what happens when you go from
within everything that happens. From that, create a model that survives. For that
So systems is an absolutely crucial concept. Right? Getting a student to think about the idea that in order to look at a problem, I have to isolate some part of the world and study it in detail. And that some part of the world is the system I'm studying to understand this phenomenon, right? So how do we get students to do that more or less automatically when they look at a problem to say, their first question should be, what's the system I need to study in order to answer my questions here? So that's my first questions. What system do we need to model to understand this phenomenon? Right? If it's a ball rolling down the hill, I need to model the ball rolling down the hill somehow. What's in, what's out of that system? Is the earth part of the system? Is the earth exterior to the system? I have to make just questions delineating the boundary of the system. What's included? That's my third question here. I went to it second because it's really critical. In order to talk about the model at all, deciding what's in, which you have to model in detail, and what's out, which you can treat just by its general effects on what it causes to cross the boundary, is very important. And then the question of scale comes up, because, as I said, I can model the human body on lots of different scales. So if I'm trying to explain a specific phenomenon, on what scale do I need to model the system in order to develop that explanation? And very often, once I've got that explanation, it will raise some questions for which I need to go to the next scale down in order to answer those questions. So figuring out what we're talking about and on what scale we're talking about it. Then, of course, a system is a collection of components. The components may themselves be subsystems, or they may be things that I can treat approximately as if they're little points. Right? So I can talk about, the kinetic theory of gases and treat the molecules as rigid spheres that collide with one another. That's a first order approximation. It doesn't explain everything, but it explains lots of things. So figuring out at what level we need to model in order to look at the phenomenon we're looking at now. You can get very far with the ideal gas laws, with the hard sphere model of molecules. We can't explain why the coefficient is different for different gases. We can get a long way. So thinking about how far down you need to model in scale and where you can make a crude approximation, what you can really oversimplify or leave out, is an important part of modeling. And then what are the roles of each component and what are the interactions between them? Those are the key systems questions to me. And you take that set of questions and ask them in context after context after context. They're going to become tools that the students have to ask for themselves when they meet a new context. And I think that's very, very important. This idea of repetitive use, developing something that is, but not repetitive use of a simple process, which is just, I do it and I don't think. Every one of these questions causes you to think. It causes you to analyze what you're looking at and try and define it better. And that's what we do when we're doing science. So these are really critical to developing a model. And we're walking around, the conversation was about you give them a model and at one point. And yes, there are many times when we, the scientists, have models we want the students to learn about. But if they haven't developed models and worked with their own conceptual structure about models, the ones we give them don't mean a heck of a lot to them. So the idea that students have to develop their own models in many circumstances before they're ready to take the models we suggest and see why we're saying this model is better at explaining this particular phenomenon means you have the idea that models explain phenomena, right? And so getting the work of developing models started early so that by the time you're trying to get them to have mental models of solids, liquids, and gases in terms of particles, those models can be built up based on prior experience of modeling and all the various phenomena that it is you're trying to describe with those models. Anybody want to add some more questions here that seem to be left out? Yes.
Well, the question of how do you talk about things differently when you are talking about them at the systems level than when you're talking about them at more elementary levels? It starts to get at a kind of a combinatorial logic of cross-cutting across cross-cutting things. So you combine this one with cause and effect, and you start to find some differences in language for talking about cause and effect when you are talking about it at the system level. So is there some sort of combinatorial logic for cross-cutting across cross-cutting concepts to combine them for more sophisticated understanding, and for teasing out things like how you would talk about systems level phenomena differently, for example, with respect to cause and effect, than if you're not talking about it with regard to the systems level?
I have a problem because I think of everything as a system.
Okay.
So, unless it's a quark, it's hard to get it not be a system. A quark or an electron may be fundamental particles. I actually have the prejudice that they are, but that's
Gotcha.
aside from the point. But everything else is a system, right? So, how big does it have to be before you call it a system?
So all discussion of cause and effect in science is with respect to the system within which something
Is occurring.
Gotcha.
Right. And if I think of it that way, then, as I said, a ball rolling down the hill is a system, right? So there's, you know, of course, an ecosystem
Yeah.
or an atmosphere is a much more complex system. And there are issues that come up with complex systems that don't come up with simple few body systems.
I was thinking
But-
about systems where you might say the whole is greater than the sum of the parts, and without reference to the whole, it's harder to have a full picture of the parts.
So I think there's really two classes. In a sense, there's systems where each subsystem is distinct and different. And and they can be very complex, right?
Right.
You can build very complex, this is a system which is made up of subsystems that you can describe in that way. Right? It can do all kinds of amazing things. But there's also the system of the atmosphere, which has actually very few distinct components, but very, very many of each of them. Right? And the kinds of things you have to think about in systems where there's very, very many of each are the ones that I think you're talking about when you say there's, because in fact, you know, this system, although it's completely built up of pieces and it's not like the atmosphere, it has emergent properties for sure. But they're designed emergent properties and much more predictable. And even a bicycle has properties that none of its components have. Right? So saying it has properties that are not the properties of the components doesn't really get at it. The issue is there's this extra feature for systems where there's so many particles that we cannot possibly specify the initial conditions in enough detail to be predictive. Right? And then I mean, emergent properties are really to do with that you know, I plant an acorn, I know I'm going to grow an oak tree, but I have no idea what shape that oak tree will take, but I'll be able to recognize that it's an oak tree and not a cypress, right? So I can predict some things, but not everything about that system. And the same is true with the weather, right? I can predict some things, but not everything. And how far forward I can project depends on how much information I've collected. But I know that the uncertainties in my predictions will get bigger the further forward I'm projecting. So those kinds of ideas about the multi-component system, I think are a higher level of system modeling that probably doesn't begin till high school. In elementary school, we're more talking about few component systems. Probably the most complex would be the matter in this table, right? And even that, we're going to model very, very crudely, right? And we're going to be concentrated. So each model is adapted to explaining a certain subset of the properties of this thing, right? And the model has, and what you really want is the ability to have and continually refine models as the way you learn science, right? I mean, I don't know anything but a collection of models, right? And I bring those models forward as I want to understand the next thing. I bring forward all the things I've already understood. I told Melanie on the bus coming here, for some reason I started thinking about how can I really describe how two hydrogen atoms form a hydrogen molecule in terms of energy levels and so on, and what's the simplest possible model. I mean, I know it's a quantum problem, I know how it really would be done, but what can I do in terms of a conceptual level description of something like that? And it's not easy, even with everything I know, it's really hard, right? So expecting that students will get it when we just tell them, well, you know, there's bonds and they form because there's an electrical structure and it goes together and they interact, it's really hard, right? So really thinking of the mental effort that goes to build meaningful models that are useful and productive for explanations and for further learning.
So part of what I was suggesting then, just very quickly, is that if you want to reach the level of a more refined, as you say, high school kids maybe getting more advanced discussion of, say, systems and system models, looking at that in the context of the other cross-cutting concepts can be a prod and aid to
Absolutely, absolutely. Just as the practices are totally entangled,
yeah.
these cross-cutting concepts entangle. I already saw, you saw some of the questions go back and forth
Yep.
across them. And yeah, you know, when you make these lists, you separate in order to define. It's the same when you make the list of the core ideas in the disciplines. We know those ideas, you know, the idea of forces and interaction and the idea of energy are not really separate ideas. They're totally interlinked, right? But you have to learn the pieces in order to put them together.
And then the links can help. It's
Right.
good to have the links. It's good that these are not mutually exclusive, because thinking about scale, thinking about cause and effect, helps you to refine your understanding of
Exactly.
systems.
And so what we did was say, what's the set which is the most powerful, the most useful in building this broader set of understandings, which are all going to be understandings built around models of systems.
Right.
Okay. Continuing. The issue of constraints. In design, it's a constraint that you put on there. In science, it's initial conditions. How does it have to start in order to behave the way I'm seeing it behave? Right? And then there's this issue of many components I bring up in this question here, going from the system, which are finite numbers of components, to the systems which are finite, yes, but very large numbers of components. And this is the emergent question also. So these are the more higher level questions that you wouldn't necessarily get into with an elementary school student. But eventually these questions become very, you know, if you want to understand climate, you have to be able to think about these levels of questions about systems too. And as I said, systems and system models, of course, connect to the practice of modeling. And the concept and the practice are not separable, but it's about using the concept to do what you need to do to develop a new model. And as I say, and I think Joe agrees, in science it's all about choosing to focus on a specific system or class of systems in order to develop some new understanding about cause and effect, about phenomena, about the way the world works. And this idea of leaving everything else out so I can focus on this. Science, you know, we live our lives with lots and lots of contradictory ideas about the world around us. We have to. I drive down the highway, and I believe that all the other drivers are going to behave according to the rules of the road. And at the same time, I'm watching out for the one who isn't. I couldn't drive if I thought that there were no rules of the road. But I have to also at the same time keep it, so in order to just live, you have to not resolve all contradictions. You have to just make a decision and move on, right? But science is the luxury of taking a system and studying it until you resolve some contradictions. It's not making the decision to do something tomorrow. It's figuring out, what do I need to figure out in order to resolve the puzzles that have been presented to me by the phenomenon that I'm observing. And it turns out that then has some useful implications. But it's not a pragmatic way to live your life. Right? You may live your life informed by science, and that's good, and I would like more of the population to live their life informed by science. But really, even the best, most informed person has to make decisions in lack of information and evidence all the time in real life. So science is a very unnatural process. And I think that's one of the things we forget when we're trying to teach it to kids. We think, because we've been doing it so long ourselves, that it's kind of natural to think this way. Well, no, it's not. It takes work, and it takes some tools. And the tool of modeling and making your thinking explicit in a model is a very, very powerful tool. And we need to help students use it and use it more broadly.
And to your second bullet point, I would add another idea that sometimes if your model doesn't make the predictions that you expect, that you know then there's something missing in your model.
Right. So the idea that a model is something that you refine and reiterate, just as you do in engineering, right? That you must, your first model isn't going to be perfect. And even your last model is going to be an approximate description. And you will have chosen to focus on certain things and leave other things out because of a particular problem you're interested in. So the next problem, you may need to change that model. Even though it worked really well for this one, you may need to refine it and add some things that you could leave out when you were worrying about this, but not when you're worrying about that. So the idea of models as fixed and forever, or flexible and iterative, is really important too. Okay. Again, this one we misnamed. The cross-cutting concept is conservation, folks.
I like that better.
Right. And then what does, now conservation doesn't mean anything unless we can say what doesn't, conservation is about what doesn't change, right? What doesn't change where? In my system, right? So in order even to talk about conservation, we don't want to talk about all the matter in the universe or all the energy in the universe. Very seldom. What we want to talk about is in this system, what energy or matter is flowing in, what energy or matter is flowing out, and what's it doing while it's in the system. How is it cycling around? What processes is it driving? So the basic idea, what makes it interesting to look at matter and energy is the fact they're conserved. And therefore, they limit what can happen. A conservation rule is useful simply because it limits possible outcomes. If I know something is conserved, then I don't have to worry about all the cases where it might change, unless it's coming in or going out. So I have to define a system and a system boundary in order to even talk about this idea. And I have to focus on, I think for students, first matter. Because conservation is a very abstract idea, and conserving something abstract is even more abstract. So conserving matter is probably something that makes a lot more sense than conserving energy early on. And understanding that that it's useful to keep track of something because it's conserved is an understanding that gets built up over time. So I have no idea, since I can't see a clock, how long I've been talking or what the time is.
1 o'clock.
It's 1 o'clock and I'm supposed to be finishing, so I'm not going to ask you to talk. I'm going to jump ahead and, again, what matter flows into or out of or within the system, what physical and chemical changes, because changes in matter do occur from an apparent point of view, even though we all know that the atoms are staying the same. It looks very different. And then the energy transfers. Now, energy, one of the reasons energy is abstract is because, in fact, most of the time we leave out most of the energy, because it's not changing. And we're only talking about what changes in energy happen. So it's the transfers and the transformations that matter. And then if we're dealing with a system, an engineering system, we have to think about inputs and outputs. And so what needs to flow in? Probably the place where kids begin to understand conservation is in a system where they see something flowing through the system and collecting. So these are my questions. I'll go on quickly. I've already said this, and I already said this is best addressed with matter first and energy second. Now I want to spend a minute or two on energy because we describe it so differently in different fields of science. I think the thing we need to do better and more often is talking about, using the language of potential energy and talking about what is the reference system. So the whole idea of having a reference system so you can talk about energy changes is critical to understanding chemical bonds, to understanding gravitational potential energy. And yet we sort of say it once when we first introduced gravitational potential energy in physics. We don't say that's what we're doing when we're talking about 1/2 mv squared as being the kinetic energy of an object. Well, actually, folks, it's not true. There's an equation in relativity that puts mass and kinetic energy together in one equation. I don't need to tell the equation to a kid, but I need to say, for the time being, I'm leaving the mass out because the mass doesn't change. And therefore, I won't worry about mass when I'm talking about energy. I'll just talk about kinetic energy and potential energy. But later on, we're going to bring the mass back in because we're going to need to. So as students move through correcting the misperceptions that we've taught because it was useful is easier if at the time we made the approximation, we'd said it enough times that they understood that it was an approximation, not an exact statement. Okay, structure and function. I think you get the point anyway, even without my next set of questions. But here, I think, you notice I come to properties. Because in chemistry, it's really not structure and function people talk about, it's structure and properties. Now, it's certainly true that once I understand properties, I can use properties to get to function. So the step between structure and function is properties. But the cross-cutting idea was it could have been stated structure, properties, and function, and it would probably have been better. Again, we chose a certain set of language. The more we work with these ideas, the more we see how they could have been formulated slightly better, and where people, not people who've worked with them a lot, but people who are meeting them and being told, okay, you should worry about structure and function. Well, some people get stuck when they say, but in my science, there's nothing about function. Right? My science is about properties. Well, yes, but that's a very closely related idea. Okay, stability and change. Again, the idea of initial conditions. The idea of feedback loops in systems. The idea that changing some parameters or conditions in the system can change the the value of many variables at the stable point is very important. Again, we couldn't possibly understand climate change without this idea. And thinking about models which can represent how changing a condition changes the stable point, which are not as abstract as the climate model, is a useful way to build towards that. So thinking about all of these questions, again, it's just a tool. It's a tool for analyzing problems. And that's what I think all of these things are. So it's a lot of questions. But obviously, which question is useful at which moment, that's for you or the student to decide. The idea is to give the students the tools. Thank you.
So we do have 5 minutes for questions, if anybody has any questions that we haven't already asked.
Yes.
I'm interested in how, I think you helped California decide to place some focus on middle school assignment of cross-cutting concepts. Teaching, were you on that committee?
Yeah, I was part of the committee. So the first actually went the other way. So the committee was asked, these are the middle school performance expectations. What's the best way to organize them? And we worked for several days actually to try and come up with what would be the most, the learning where learning this year builds on that year. And we worried about math because of course 8th grade math is quite different from 6th grade math, and what would fit at what grade level from that point of view, what was conceptually more complicated or less, and came up with a sequencing of core ideas. And then we saw that given that sequencing of core ideas, it was natural to say, well, in this year stress these 3 cross-cutting concepts, and in the next year stress those. It was not driven by start from the cross-cutting concepts and then decide what core ideas fit. It was decided by sequencing the core ideas into a logical learning sequence, and then saying, well, if this is what you're doing, of course you could always put all of the cross-cutting concepts there, but to make sure that all of them got touched at some point, we said, well, stress these 3 this year, and those 3 that year, and another 3, and each one of them appeared twice by the time we were done.
I like the way that turned out. Hopefully we'll do something similar.
Yes.
So, given that most college freshmen are coming from a K-12 system that
didn't do any of this.
Yeah, that didn't do any of this right now. So what do you see as the most important change that, we can do in higher ed to kind of jumpstart 3D learning, 3-dimensional learning?
Well, first of all, you have to decide that 3-dimensional learning is important at the college level, which I would say it is, right? Having decided that, then I think, again, just as you would at the elementary level, it's developing a curriculum where it integrates naturally, right? So developing and that works back from what are your learning goals for a course, which of the practices are being stressed where in your course, how you design your lessons. They are lessons, even if you think of it. I mean, to go from the idea of planning a lecture to designing a lesson is already a step, right? and thinking about how you build it across your 4 years is hard because there's not one path through the curriculum for all these students, right? So I don't pretend it's going to be easy, but I do think that just as these are tools for thinking for kids K-12, they're really critical tools for thinking for students studying science in college. And we need to move towards thinking more about, we live in an information-rich world. Information is cheap and easy to find. What you need to be able to do is evaluate, and communicate it, right? What you need to be able to do is process it and use it in useful ways, which is what the rest of the practice is, right? And ask the question that takes you to the next piece of information. Right? If you're not a scientist, you're not discovering new ideas, then you're using these as tools to negotiate through the world of ideas that other people have discovered. Yes.
Okay. So my question is about the role of knowledge, not necessarily scientific knowledge, but knowledge about the nature of science and knowledge about epistemic aspects, which is, I think, what a lot of these cross-cutting concepts are getting at, but are very challenging for people who are less familiar with science. So for example, I work a lot at the elementary level, so teachers who are teaching science at the elementary and perhaps middle school level, but even for kids, I'm wondering how to support them a little bit better without
How do you get to metacognition, right? I mean, engaging in the practices is doing science at some level.
It's not
doing original science, but for the kids, it's doing science, right?
Right.
And so kids' reflection on the nature of science must be about, what do I do when I do science in my science classroom?
But it's also about values of science, such as wanting to look for mechanism, or thinking it's valuable and important to look for mechanism. And how do you do that? Or how do you look for cause and effect? What's the value of patterns? Because in the 60s, patterns was all about sorting buttons in science. It wasn't about finding patterns to figure out the cause of.
Yeah, well, you can misapply any concept.
Sorting buttons.
No, I mean, students that were observing nothing, basically, right? I mean, making detailed observations where detailed observations weren't useful, or whatever. You can make a travesty of any idea. So I don't know how you prevent that, but what you're trying to do is the opposite. You're trying to support teachers to help students not only incorporate these ideas into their thinking, but to think about their thinking and recognize what they're doing. Right?
And when
you can't have
questions
them
are important, and when to use them, and how to value them, and how to
right.
do them.
And I think you only learn by doing in these cases. I think metacognition comes later. You have to have some experiences in order to think about how you think and what you do. Right? So I think building the experience base is what elementary teachers need to be more concerned about. And yes, the kids will get the idea that in science we ask questions, right? In science we measure things. So the kids will gradually begin to have their own view of what you do when you do science. And I think if they're kids who've engaged in all of these practices and been introduced to these cross-cutting concepts as tools for thinking, their ideas of what science is will be much richer. The level of having a conscious view of what science is, taking the time to talk about what is science and how do I think about it and why are these things useful, that's another level up. And it takes building a base before you're ready for it. Exactly when you're ready for it, I'm sure you're ready for it at some level in kindergarten. But the level at which you can do it depends a lot on what experience you're building from. So figuring out when's the time to step back and say, well, why did we do it that way? Or what did we do yesterday that we might try again tomorrow? Those kinds of things can be introduced in simple ways at the lower grades and in more sophisticated ways later, but it's a judgment call every time when you're going to do it. So that's the art of teaching, right, is to make those judgment calls. And you're making many of them in every lesson.
So we actually have run out of time now. So before we say goodbye, I'd like to give you this commemorative mug.
Create for STEM, that's great.
And a thank you note from all of us.
Thank you.
Please join me again in thanking Helen for.
So hold on, so I don't know if it's on this, if people know about this, but Helen's going to be available to talk particularly with the teachers that might be in the audience from 1:30 till 2:30, I believe, Pete?
Yeah.
1:30 to 2 in this room for our teachers or others going around.
So actually for now,
Right, so Pete,
I'm staying around and.
And also, the slides will be posted this afternoon on the Create website and the materials, and we'll be posting this video on South End.
That was wonderful.